Hello friends, IBM is here with another episode of Learning Physics. Please Happy New Year 2023 for those who are seeing this video for the first time. Happy New Year. IBM is here with episode 2 of waves. We are actually looking at waves and superposition, and this is going to be strictly part 2 of sort of the past paper questions. Remember, this is AS Physics, that is Physics 9702. Advanced, it is actually advanced subsidiarily structured equations. You'll expect to find most of these questions in paper 2, but of course, for a particular topic, the same concepts can be used in paper 1 for the same topic. This is actually part 2 of waves and superposition. Remember what I said in part 1, I said this topic is the most important topic in AS. If you pass waves and electricity, then you are good enough to go as far as AS physics is concerned. So this is part 2. Remember, in these videos of waves, we are going to see or to discuss questions relating to longitudinal and transverse waves. We shall see questions about Doppler effect, electromagnetic waves, superposition and stationary waves, diffraction, and a lot more. So do not forget to subscribe, share this video with friends, download the document from the video description to help you practice these questions so that you get enough confidence. Without wasting any more time, I would like to take you to the document of the past paper questions so that we start solving them in this part 2. So the last time in part 1, I remember we must have stopped on, it must have been page 459, I guess. 459, yes, around here. Part 1 stops on this particular question. I think we had solved this. We had stated the conditions for the formation of a stationary wave, where we say two waves of the same type, same frequency, same wavelength, traveling at the same speed in opposite directions overlap, form a stationary wave. We had answered this question also, I guess, and I mentioned and said I'll record a specific video about these concepts of time base and so on and so forth. So I think we stopped on question C and the video stopped there abruptly. So let's start with question C. The loudspeaker in B is held above a vertical tube of liquid as shown in the figure. A tap at the bottom of the tube is opened so that the liquid drains out at a constant rate. The wavelength of the sound from the loudspeaker is 0.18 meters. The sound that is heard first becomes much louder when the liquid surface reaches level A. It becomes much louder. So it means we have the first harmonic when the liquid level is in position A. That's where we have the first harmonic. So we have a node here. And you will notice that this length L, I'll call this L1, is representing a quarter of a wavelength. Remember, a full wavelength, we would have two loops like this. A full wavelength, but now we have just a quarter a loop, something like this. So that is a quarter wavelength. L1 is representing a quarter a wavelength. The sound that is heard first becomes much louder when the liquid surface reaches level A. So we expect that on level A there must be a node, of course, because the first resonance occurs there. The next time that the sound becomes much louder is when the liquid surface reaches level B. So the next one will be when the liquid level reaches surface B, where we shall have something like this. In this case, you'll notice that the length L2 is a half plus a quarter, which is 3/4 wavelength. So L2 is going to be 3/4 wavelength. So again, at level B, we have another node. The second resonance occurs at that level. Okay, calculate the distance, the vertical distance between level A and level B. So the vertical distance, we shall get L2 minus L1, that is this distance here is L2 minus L1. So the distance is L2, which is 3 over 4 lambda, minus L1, which is 1 over 4 lambda, which I think is 2 over 4 lambda, which I think is lambda over 2. And since the wavelength is 0.18, so this is going to be 0.18 divided by 2. And of course, that is 0.090 in meters. So the distance between level A and level B is 0.090 in meters. Then on the figure 4.3, label with the letter N the positions of the nodes of the stationary wave that is formed in the air column when the liquid surface is at level B. So if the liquid surface is at level B, so we shall have this node here and this node here. You can see what I've drawn here. So we write N in that line and another N in that line. So those are the positions of the nodes. Then the mass of the liquid leaving the tube per unit time is 6.7 grams per second. The tube has an internal cross-sectional area of 13 centimeters squared. The density of the liquid is 0.79 grams per centimeter cubed. Calculate the time taken for the liquid to move from level A to level B. So we want the time taken to move from level A to level B. Okay, so first of all, we know that mass equals to density times volume. If I divide both sides by time, so this is mass per unit time, which we have. And therefore, we remain with this T here as the subject because we want the time taken. So the time taken, ta is going to be equal to density times volume. Remember, volume is cross-section area times the length or the distance, which I'm calling L. So then this is going to be divided by mass per unit time. That is going to be our value of T. So T is going to be density. The density is 0.79. I'll add the units so that people see that they cancel out. Grams per centimeters cubed times the cross-sectional area is 13 centimeters squared times the length is down the distance through which the liquid moves, that is 0.090 meters. In centimeters, we multiply it by 100, so it becomes 9 centimeters divided by the mass per unit time. The mass per unit time is 6.7 grams per second, so that is 6.7 grams per second. Of course, you must have noticed that actually the units have already cancelled out. Grams has cancelled. Per centimeter cubed has cancelled all those units, so you remain with 1 over per centimeter, which is 1 over per second, which is simply seconds. And when I press my calculator to verify the time, 0.79 times 13 times 9 divided by 6.7. So this gives me value of time as 13.796, which is approximately 13.8 in seconds. Okay, so that is 13.8 in seconds. By reference to the direction of propagation of energy, explain what is meant by longitudinal propagation of energy. We have already seen that vibration of particles Vibration of particles for a longitudinal wave, vibration of particles is parallel to the direction of propagation of energy. Vibration of particles is parallel to the direction of propagation of energy. That is for longitudinal waves. For transverse waves, the vibration of particles is perpendicular to the direction of propagation of wave energy. A car horn emits a sound wave of frequency 800 Hz. A microphone and a cathode ray oscilloscope are used to analyze the sound. I am going to record a video specifically about the cathode ray oscilloscope. The waveform displayed on the CRO screen is shown in the figure. Determine the time-based setting. So we know that period is equal to 1 over frequency, which is equal to 1 over 800. That is the period. But like I said, my students always prefer to use T equaling to Lx, where T is the period, L is the length representing one cycle on the screen or on the display, and X is the time-based setting. So we now know T. All we need is L. So T is 1 over 800 equaling to L. Let's find L. So each 5 small squares represent 1 centimeter. 1, 2, 3, 4, 5. That is 1 centimeter. 1, 2, 3, 4, 5. Those are 2 centimeters. 1, 2, 3, 4, 5. Those are 3. 1, 2, 3, 4, 5. Those are 4. And these 5, those are 5 centimeters. So 5 centimeters are representing how many cycles? If I start from here, the next time I come about here, that is 1 cycle. So that means this is the second cycle. So those are 2 cycles. So the length for 1 cycle is going to be 5 over 2, which is 2.5 centimeters. So L is 2.5 centimeters. So this will be 2.5 centimeters multiplied by X. So what is X? X is therefore going to be 1 over 800. Remember, this is in seconds. Divide by 2.5. Remember, this is in centimeters. So I just press my calculator. So from my calculator, I'm getting the time-based setting as exactly 5.0 times 10 power negative 4. The intensity I of the sound at a distance r from the car horn in B is given by the expression I is equal to k over r squared. Intensity I of the sound at a distance r from the car horn. So if the car is at x, at point O, the distance r is equal to, when the car is at x and the observer is at point O, it means the distance from x to O is equal to 120 meters. When the car is at point Y and the observer is still at point O, the distance from Y is equal to 30 meters to the observer. An observer stands at point O. Initially, the car is parked at point X, 120 meters away from point O. So the distance Rx is 120. The car then moves directly towards the observer and stops at point Y, a distance of 30 meters away from the observer. The car horn continuously emits sound when the car is moving between X and Y. The sound wave at point O has amplitude AX when the car is at X and amplitude AY when the car is at Y. Calculate the ratio AY over AX. So we have already seen that the distance, first of all, using the first equation, that I is equal to K over R squared. we are going to use x when the car is at x, we use rx, and ry when the car is at y. So dividing two equations, for x it will be ix equals to a constant k divided by rx squared, and I'm dividing by another equation for at position y. So divide by, for y, this will be k divided by ry squared. So this is giving me that ix over iy is equal to ry over rx, but this is going to be squared because of these squares on rx squared and ry squared. You see that I get a reciprocal because this was division. You also notice that when you divide these two equations, k cancels out. So that is one equation. Number two, we also know that intensity is directly proportional to amplitude squared. So intensity at x is going to be amplitude at x squared, and intensity at y, whether there is a constant, so I'm dividing by intensity at y, which will be equal to a constant times the amplitude at y, and that is squared, and the constant k has cancelled out again. So I also have that ix over iy is equal to ax squared over ay squared. So I'm going to equate this equation to this one. Therefore, it is going to imply that ax squared over ay squared is equal to ry over rx, and this is squared. There is a square on both sides, so the square goes off. We get the square root both sides. But remember, we want the ratio ay over ax, so I get the reciprocal both sides. So ay over ax is going to simply be rx over ry. Remember, rx was 120 and ry was 30. So this is giving us automatically 4. So therefore, the ratio is 4. So I have used the long algebra, but you could have a shortcut. So that is just because I want the PCB students also to try and follow through this algebra. The algebra is not physics, it's simply mathematics. Okay. So that is the ratio ay over ax. I hope people will remember to get the reciprocal as required. When the car is parked at x, the frequency of the sound from the horn that is detected is 800 Hz. That is normal frequency. As the car moves from x to y, the maximum change in the detected frequency, maximum change. So it means the highest frequency is going to be 800 plus 16. The speed of the sound is 330, determined to two significant figures, the minimum wavelength of the sound detected. So we know from the general wave equation, V equals to lambda f, we want wavelength. Wavelength is minimum when frequency is maximum because they are inversely proportional. So minimum wavelength, lambda minimum, is going to be V over f maximum. So V is 330 and the maximum frequency is 800 plus 16. So I just press my calculator. And from my calculator, the wavelength is 0.40 to two significant figures. 0.40 to two significant figures. Then determine to two significant figures the maximum speed of the car. Maximum speed. So, of course, F, we know that observed frequency is equal to V over V minus Vs times Fs. Of course, speed is maximum when the observed frequency is actually maximum. That's why of course, speed is directly proportional to f. Speed is maximum when the observed frequency is maximum. So the observed frequency is maximum, which is 816. I am putting here subtraction because it's moving towards. Frequency is maximum when the source is moving towards the observer. If it was away, it would be plus to make the numerator larger. So this is going to be equal to V. V is, remember, 330. Then times Fs, the normal frequency is 800, divide by 330 minus the speed Vs. So what remains is just to cross multiply, or to have 330 minus Vs is equal to 330 times 800 over 816, depending on which mathematics you can use. 330 times 800 divided by 816. So I take minus Vs to the right, so the other one I subtract. So 330 minus the answer. So I obtain Vs as 6.47, or approximately 6.5 meters per second. So that is the maximum speed of the car. State the difference between a stationary wave and a progressive wave. I think we have mentioned such a difference. We know that a stationary wave, there is no transfer of energy from one point to another. A progressive wave, energy is transferred. So you just simply say in a stationary wave, energy is not transferred. Which means that it is transferred in a progressive wave. So you can say, oh, in a progressive wave, energy is transferred. So that is the difference. In a stationary wave, energy is not transferred. In a progressive wave, energy is transferred. Then state the difference between a stationary wave and a progressive wave in terms of phase of two adjacent vibrating particles. Two adjacent vibrating particles, that is neighboring particles. In a stationary wave, two neighboring particles must be vibrating in 180 degrees. They must be vibrating in phase. But yet for progressive wave, two neighboring particles cannot vibrate in phase. They actually vibrate out of phase. So you can say in a stationary wave, particles, that is the adjacent particles, are in phase. Remember I said if you have now these as two segments for stationary wave, particles between two nodes, those are neighboring particles. Here they are vibrating in phase. However, an antinode and an antinode, particles in two different segments vibrate 180 degrees out of phase. But particles between two nodes are always vibrating in phase. Therefore, neighboring particles are always in phase. Or you would say in a progressive wave, adjacent particles are not in phase. So that is the major difference. For progressive wave, two adjacent particles cannot be in phase, but for stationary wave, two adjacent particles vibrate in phase. A tube is open at both ends. A loudspeaker emitting sound of a single frequency is placed near one end of the tube. So it is an open tube. We see an antinode, an antinode, an antinode, and an antinode. At every open end is an antinode. Between every antinode, there must be a node. There must be a node. Between every antinode, there must be a node. The speed of the sound in the tube is 340 meters per second. The length of the tube is 0.60 meters. Maybe we can try to sketch this. Remember, at every antinode, particles vibrate with the maximum displacement. So I'll draw something like this. At every antinode, particles vibrate with the maximum amplitude. You can even see in the diagram. A stationary wave is formed with an antinode A at each end of the tube and two antinodes inside the tube. State what is meant by an antinode of the stationary wave. Remember, we said an antinode is a position. It is not a particle. It is a position where particles have maximum amplitude or vibrate with the maximum amplitude. So position where particles vibrate with the maximum amplitude. We can't say particles vibrate with maximum displacement because amplitude itself is maximum displacement. For stationary wave, all particles do not have the same maximum displacement. Each particle may have a different maximum displacement ranging from 0 to a certain value. So that's why we are saying maximum amplitude. Amplitude itself is maximum displacement. So particles in a stationary wave each has a different maximum displacement. So it has a different amplitude. Yet, for a progressive wave, particles must reach the same maximum. In other words, particles have the same maximum displacement in a progressive wave, which is not the same case with a stationary wave. Set the distance between a node and an adjacent antinode. Distance between a node and an adjacent antinode. I want you to notice that the distance between we have 1, 2, 3. So we have 3 times the distance between adjacent nodes is equal to 0.6 because the length between the first and the last antnode is 0.6. So we have that 3 times the distance between a node and a node, an antnode and an antinode is equal to 0.6. Therefore, it doesn't require you to be as genius to see that the distance between a node, between two adjacent antinodes, distance between two adjacent antinodes is 0.6 divided by 3, which is 0.2 meters. But that's not the answer to this question. We want the distance between a node and an adjacent antinode. That is a node and a neighboring antinode. You see that the distance between a node and an antinode is a half of the distance between an antinode and an antinode. So the answer we need here, the distance between a node and an antinode is equal to a half. the distance between two adjacent antinodes, that is a half of 0.2, and that is giving us 0.10. So the distance is 0.10. Remember where I go to the 3, this is 1, this is 2, this is 3. So we have 3 times the distance between an antinode and the next antinode. And the total length there is 0.60 meters. Then determine for the sound in the tube the wavelength. So we also know that the distance between a node and an antinode is a quarter wavelength, or we know that the distance between two adjacent antinodes is half wavelength. So we can find the wavelength. So I can say distance between antinode and antinode is equal to a half wavelength, and that distance is 0.2. Or I can say distance between, so this is 0.20, which means wavelength is 0.20 times 2, which is 0.40. Alternatively, method 2, I can say the distance between a node and an antinode is a quarter of wavelength. Remember, this distance is 0.10, which means that lambda is 4 times 0.10, which still gives you the same answer as 0.40 meters. Then determine for the sound in the tube the frequency. Since I have the wavelength and I think I have the speed as 340, then the frequency is easy to find. Frequency by the general wave equation is equal to V over lambda, and V is 340 divided by the wavelength, which is 0.40. When I press my calculator, so this is 850. So that is the frequency. That is the frequency here. Determine the minimum frequency of the sound wave from the loudspeaker that produces a stationary wave in the tube. We want the minimum. When you look at this, you will notice that these are how many harmonics? This is a half plus a half plus another half. There are 3 halves. That is 1 cycle and a half. That is 1 cycle and a half. So the fundamental would be there, and okay, I'm looking for just a simple of representing this. But you would notice that this is 3 times F naught, 3 times the fundamental. If this is an antinode, those are 3 loops, or 3 times the fundamental. But anyway, if that is hard for someone to see, okay, let me begin with that. We know that Fn is equal to n times F naught. We have we have got actually the third, that is representing the third harmonic. So we have that F3, which is 850, is equal to 3 times F naught. So you would see that F naught is equal to 850 divided by 3, which is 850 divided by 3, which is 283, approximately 280 hertz. Alternatively, I can look at this right away from the diagram, that this is, here I have a quarter plus a half plus, that is a quarter plus a half plus a half plus a quarter. So you have a quarter, a cycle, plus a half, a cycle, plus a half, a cycle, plus a quarter. That is 1 plus a quarter, plus a half, 1 plus a half, I think that is 3 over 2. Three over 2 wavelength. That is 3 over 2 wavelength. So L here is representing 3 over 2 wavelength. I'm using method 2. So frequency is equal to V over lambda. But L is representing 3 over 2 wavelength from the graph, which means that the wavelength is going to be twice L over 3. That the wavelength will be representing twice L over 3. And remember, L is 0.6, so this is going to be 2 times 0.6 divided by 3. So this means, oh no, this is taking me back to the same thing. This is not necessary. This is not necessary. I want the fundamental. I'll sketch here the fundamental mode. For the fundamental mode, we have one antinode and another antinode plus one node. So this is going to be something like this. And for the fundamental, this is L would represent a quarter plus a quarter, that is half wavelength. Yes, half wavelength. So it means wavelength is going to be representing 2L. Wavelength would be representing 2L for the fundamental mode. So this is going to be 340 divided by 2L, which is 2 times L, which is 0.6 for the fundamental mode. Yes, that is the easiest. 340 divided by 1.2. This is still going to be 283.33, which is approximately 280 hertz. Okay, so for an open pipe, the fundamental mode has two antinodes and one node at the center. And this is a quarter cycle plus a quarter, which is half a wavelength. So L represents half a wavelength. That's why I'm saying L wavelength will be twice L. A horizontal string is stretched between two fixed points X and Y. The string is made to vibrate vertically so that a stationary wave is formed. At one instant, each particle of the string is at its maximum displacement as shown in the figure. So at this point, each particle is at its maximum displacement. Remember, the particles do not have the same maximum displacement. So I'll draw another envelope. Because we are used to these loops when answering these questions, they guide us so much. P and Q are two particles of the string. The string vibrates with the frequency for it has distance. XY is 20. We have 1, 2, 3, 4, 5 loops. Remember, at X there is a node, at Y there is a node. So there is an antnode here, an antnode here, an antnode here, an antnode here, an antnode there. There is a node at this point, a node here, a node here, a node here. So there is a node, 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 node. State the number of antinodes in the stationary wave. So we have 1, 2, 3, 4, and 5. So the number of antinodes is 5. Determine the minimum time taken for the particle P to travel from its lowest point to its highest point. To travel from its lowest point to its highest point. I think that is half a cycle. If this is your lowest point and this is your highest point, for one complete cycle, if this is A and that is B, the particle has to go from A to B and back to A for one complete cycle. But if it simply moves from A to B, that is half a cycle. So the time we want is half a period. So the time here is going to be a half of a period. Half a period, and what is the period? The period is 1 over frequency. Period is 1 over 40. So it means the time we want to talk about here is going to be a half of a period, which is 1 over 40. So that is 1 divided by 80. And this is 0.1, I mean 0.125 seconds. So 0.0125 seconds, or 1.25 times 10 power negative 2 seconds. Alternatively, you can write that. State the phase difference with its unit between the vibrations of particle P and particle Q. Remember, they are forming a stationary wave. Particle P is in this loop, this segment. Particle Q is in the other segment. Particles in two adjacent segments for a stationary wave vibrate in what we call the antiphase, 180 degrees out of phase. Therefore, the answer here is 180 degrees, or simply pi radians, because they are in neighboring adjacent loops or segments. They are 180 degrees out of phase. Remember, particles in the same loop vibrate in phase. The phase difference is 0. But particles in two neighboring loops vibrate in 180 degrees out of phase for a stationary wave. Then determine the speed of a progressive wave along the string. Speed. From the general wave equation, v, which is the speed, is equal to lambda times f. We need to find L. We need to find the wavelength. Let's look at the graph. We have 1 cycle, 2 cycles, and a half cycles represented by that length. So the length L, which is 2 meters, 2.0 meters, is representing 5. Is it 5 over 2? 2.5 is 5 over 2. 1 cycle, 2 cycles and a half. 2.5 cycles, 2.5 wavelength, that is 5 over 2 wavelength. So 2 meters is having or is giving us 5 over 2 wavelength. 2 meters is giving us 5 over 2 wavelength. That means the wavelength is going to be 2 times 2.0 divided by 5. That is our wavelength. And we have already the frequency, so we just substitute to find the speed. So the speed v is going to be the wavelength, which is 4.0 over 5 after multiplying 2 times 2.0. Then times the frequency, which they gave us as 40. So 4 times 40 divided by 5. And this gives us the speed as 32 meters per second. So that is the equation. Two sources S1 and S2 of sound are situated 80 centimeters apart in air, as shown in the figure here. So there are two sources, S1 and S2. Before we even go any further, we need to find, I think M is the position for the observer or the detector. The frequency of vibration can be varied. The two sources always vibrate in phase. Phase difference between the sources is 0. If they always vibrate in phase, they are coherent. They maintain a constant phase difference. The microphone M is situated a distance 100 centimeters from S1 along a line that is normal to S1, S2. Let's first find the distance S2M. We know S1M. We need to find S2M, this distance here. Of course, this is a triangle. Pythagoras theorem gives us this distance as the square root of 80 squared plus 100 squared, which is, I think that is 120. 80 squared plus 100 squared under square root, that is approximately 128 centimeters. So S2M is 128 centimeters. That is S2M. Okay. As the frequency S1, S2 is gradually increased, the microphone M detects maxima and minima of intensity of sound. State the two conditions that must be satisfied for the intensity of sound to be zero. That is minima, destructive interference. First of all, for destructive interference to occur, the path difference must be any odd number multiple of half wavelength. Or we say the path difference is going to be n plus a half of wavelength. Number two, for total cancellation, because the resultant is zero, then the amplitudes of the two waves must be the same. Since intensity is directly proportional to amplitude squared, if the amplitude is the same, we could also say the intensity at M is the same. So amplitude is the same or the intensity is the same at A. Amplitude or intensity of the waves at M is the same. So same amplitude or same intensity of waves at point M. That will result into total destructive interference. But what is the condition for destructive interference? The phase difference or path difference. Let's start with path difference between the two waves. The path difference between waves from S1 and S2 is, I can say, a half lambda, or any odd number multiplied by half wavelength, or I can say half lambda, or I can say n plus a half of lambda. That is the expression for the path difference for destructive interference. So this is general. This is the first order minima. Or I can talk about phase difference. The phase difference between waves from S1 and S2 is half wavelength, that is half a cycle, that is pi, or 180 degrees. So this is 180 degrees because lambda is 360 degrees. So half lambda is 180 degrees. And 180 is pi. Also, somebody would also say pi radians. Pi radians. That is the phase difference for destructive interference. Or it can be n plus a half times 360 or times pi over 2. Yes, times 360 or times 2 pi. That is the phase difference, which gives us destructive interference. Okay, so you can state which one is easier for you. The speed of sound in the air is 330. The frequency of the sound from S1 and S2 is increased. Determine the number of minima, that is destructive interference. Determine the number of minima that will be detected at M as the frequency is increased from 1 kilohertz to 4 kilohertz. First of all, remember the general wave equation, V equals to lambda F. We are dealing with sound of that frequency. So we can first of all find the corresponding wavelengths, because the wavelengths are going to help us to find how many minima are observed in this case. So for 1000 kilohertz, what is the wavelength? The wavelength is going to be equal to 330 divided by 1000, and this is going to be, I think, 33 centimeters or 0.33. So this is 33 centimeters. This was in meters. I multiply by 100, it becomes 33 centimeters. That is lambda 1. Then lambda 2, when the frequency is 4 kilohertz, this is 330 divided by 400,000, and this is going to be 330 times 100. So this is 8.25. So the wavelength is in that range, 8.25 and 33 centimeters. So when we are checking, we need only minima within that range. So one, we find the path difference. Path difference. Path difference between the waves. What is the path difference between the waves? So the wave which moves from S2 to M takes that distance. The wave which follows from S1 to M takes 100. So the path difference is the difference between S2M minus S1M, which is 128 minus 100, which is 28 centimeters. So the path difference is 28 centimeters. Path difference is 28 centimeters. Then the wavelength changes. The wavelength changes between 33 centimeters to 8.25. 8.25 centimeters. So we know that range. But then we know for minimum, the path difference must be equal to n plus a half times lambda. So let's now start our test. We start our test. We start with n equals to 0. Zeroth order. Is it formed? What is lambda? When n equals to 0, lambda is going to be, remember the path difference is 28. So lambda is going to be equal to 28 times 2, which is 56 centimeters. This is outside that range, so we ignore it. Then let's check the next. For n equals to 1, what is lambda? When I put here 1, this is going to be 1 plus a half, which is 3 over 2. So lambda becomes 28. Remember, path difference is 28 times 2 over 3. I just substituted for n with 1. So it becomes 1 plus a half, which is 3 over 2 lambda. Remember, this is equal to path difference, which is 28. So I cross multiply 28 times 2 divided by 3. And this gives me 18.7 centimeters. And 18 is in that range, so that one is formed. We check n equals to 2. For n equals to 2, what is lambda? You notice that lambda is going to be 28 again times 2, this time divided by 5, because it will be When I put 2 for n, it will be 2 plus a half, which is 5 over 2. So if it is 5 over 2, then I cross multiply, it will be 28 path difference times 2 divided by 5. And this gives me 11.2 centimeters. You see that 11 is still within the range of the wavelength, so that is formed. We can check n equals to 3. Lambda is therefore going to be 28 times 2 divided by, when n is 3, we have 3 plus a half, that is 7 over 2. So this is divided by 7. And this is equal to, I think, 28 is 4. So that is 8. 8 centimeters is below 8.25. So that is not formed. So it means for other values of n, the wavelength will not be in that order, so it will not be formed. Therefore, the number of orders we have 1 and 2. So there are only 2 orders. The number of orders are only 2. So that is our answer there. So this one will be eliminated. It is not formed, and for n equals to 0, it is also not formed. So it is only n equals to 1 and n equals to 2 which are formed. So there are two values of n, so there are 2 orders. A double slit interference experiment is set up using a coherent red light as illustrated in the figure. Coherent red light. So we have a double slit here. And if it is a double slit, the first thing to come into your mind is Young's double slit equation. Lambda is equal to AX divided by D. State what is meant by coherent light. Coherent light. So what do we mean by coherent light? So coherent light would mean constant phase difference between light waves, or light waves which have a constant phase difference between them. So this one means constant phase difference between light waves. Constant phase difference between light waves. That's what we mean by coherent light, or light waves that have or that maintain constant phase difference between them. Estimate the separation of darker fringes on the screen. Separation of darker fringes on the screen, that is x. From the equation, lambda is equal to ax over d. We want x. So using red light, because they told us it is coherent red light, since the wavelength has not been given, we can choose any wavelength of red light. So x is going to be equal to lambda times d over a. So I said you should be able to know the range of wavelengths. So for violet is 400 nanometers up to red, which is 700 nanometers. But it's not exactly 700. Actually, it's not only 700. Because when you look at the rainbow, the wavelengths just simply fade. From red, it goes down to lower values of red wavelength until we reach orange. So you can have values between 640 to 700 nanometers for red light. So I'll take 700. Wavelength is 700 nanometers. That is 700 times 10 power negative 9 times d. They gave us the distance between the slits and the screen as 2.4. Divide by the slit separation. They gave us the slit separation as 0.86. So we divide this by 0.86 times 10 power negative 3. From my calculator, I get 1.95. millimeters. I said you could choose another value for wavelength. Another person would find x as wavelength using say 650 times 10 power negative 9, then times 2.4 for d, divide by 0.86 times 10 power negative 3. This person would get a value slightly different from this. For example, so this would be 1.8 times 10 power negative 3, which is approximately 1.8 millimeters. This would also be accepted because they didn't give us an exact value for the wavelength of red. So we can choose any value around red between 640 to 700 nanometers. Initially, the light passing through each slit has the same intensity. So initially, intensity is the same for the light passing through each slit. That means the amplitudes were the same because remember, intensity is directly proportional to amplitude squared. The intensity of light passing through one slit is now reduced. So it means now the amplitude of light from one of the slits is no longer the same as the amplitude of light from the other slit. What does that mean? Total destructive interference is not observed. We cannot have we cannot have total destructive interference. There is no total cancellation. What does that imply? It means, first of all, if the intensity is reduced, it means the brighter fringes will be less brighter because the intensity has been reduced. But the darker fringes, since there is no more total cancellation, the darker fringes will no longer be extremely darker. They will be lighter, if I'm to put it like that. So there is no longer complete destructive interference. There is no longer complete destructive interference. There is no longer complete destructive interference. Reason, as amplitudes are no longer completely cancelled, as amplitudes no longer completely cancel. The amplitudes no longer completely cancel out because they are not equal. So the darker fringes will be lighter. Since we want to talk about only dark fringes, so dark fringes are lighter. In other words, they're not as completely dark as they were before. Since there has been a reduction in the intensity, it also would mean that the brighter fringes will be less brighter. Okay, define the frequency of a sound wave. Of course, frequency refers to the number of oscillations. The number of oscillations, because the frequency depends on the source. So the frequency of a sound wave is the number of oscillations of the source. Of the source of sound, and that is per unit time. other words, number of oscillations per unit time, but remember for a sound wave, the frequency depends on the source. So the number of oscillations of the source of sound per unit time. A sound wave travels through air. Describe the motion of the air particles relative to the direction of travel of the sound wave. Of course, sound being longitudinal, we know that the particles of a longitudinal wave vibrate parallel to the direction of propagation of energy or to the direction of propagation of the wave. So we know that air particles vibrate parallel to the direction of travel of the wave. Because sound is longitudinal, air particles vibrate parallel to the direction of travel of the wave. The sound wave emitted from the horn of a stationary car is detected with a microphone and displayed on a cathode ray oscilloscope as shown. Okay. The y-axis setting is 5.0 millivolts per centimeter. The time-based setting is 0.50 milliseconds per centimeter. Use figure 5.1 to determine the frequency of the sound wave. Of course, to find frequency, we need the period. We need to find the period. And remember, I said the period is going to be L times X. L is the length representing one cycle, and X is the time-based setting. So let's look for one cycle from here. I will draw a horizontal line within the wave so that it is easier for me to find one cycle. One cycle is easy to find, I guess. If we start from here, one cycle stops here. This is 1, 2, 3, 4, 5. That's 1 centimeter. 1, 2, 3, 4, 5. Those are 2 centimeters. So there are 4 centimeters representing one cycle. So the period is going to be 4 centimeters times the time-based setting, which is 0.50 milliseconds per centimeter. So per centimeter cancels out, and this gives you 2 milliseconds. So the frequency is going to be 1 over t, where t is 2 times 10 power negative 3. One divided by that, I think this is 500 without calculation. This is 500 hertz. You can just verify 1 divided by 2 exponent negative 3. So from my calculator, the frequency is 500. The horn of the car sounds continuously. The horn of the car sounds continuously. Describe the changes to the trace seen on the CRO as the car travels at a constant speed. So V is constant. Direct it towards the stationary microphone. So remember, frequency F is equal. Observed frequency is V over V minus, it is directed towards. So it is V minus Vs times Fs. So because it is towards, the horn of the car sounds continuous. That's why the changes to the trace seen on the CRO as the car travels at a constant speed, directed towards the stationary microphone. So if it is towards the stationary microphone, the frequency is higher. So F naught is increasing if it is towards. If F naught is increasing, remember period is inversely proportional to F. If F is increasing, the period is decreasing. And Of course, when the source is moving towards the observer, the amplitude increases, because um, we know that intensity is directly proportional to amplitude squared, and we also know that intensity is inversely proportional to the square of the distance from the source. So whenever the source distance becomes smaller, the intensity increases, and when the intensity increases, the amplitude increases, and amplitude is loudness. So number one, we can say, okay, the time period reduces, time period decreases. We have seen why it decreases. Period is inversely proportional to frequency. When it is towards frequency is higher, the period is smaller. So the time period decreases. In other words, the peaks get closer. Number two, we have seen intensity is directly proportional to the amplitude, but intensity is also inversely proportional to the distance from the source. When it is towards, the distance from the source to the observer is reducing. When the distance reduces, the intensity increases. When the intensity increases, the amplitude increases. So we say amplitude increases. Directly away from the stationary microphone. Directly away. Of course, if it is away, the equation of frequency changes. Frequency decreases. So when frequency decreases, it means the period increases. So number one, time period increases. Time period increases. Number two, when it is moving away, the distance of the source from the observer is reducing, which means, is increasing. That is, I is inversely proportional to the square of the distance. When the distance increases, intensity decreases. And when the intensity decreases, remember intensity is also directly proportional to amplitude squared. When intensity decreases, amplitude decreases. So here we simply say that the amplitude decreases. The amplitude decreases. Interference fringes may be observed using a light-emitting laser to illuminate a double slit. The double slit acts as two sources of light. Explain the part played by diffraction in the production of the fringes. You and me will note that diffraction means spreading of light waves. Spreading of waves into regions of geometrical shadow. So the role played by diffraction is actually relating to spreading. Therefore, diffraction, the part played by diffraction, we know that waves at each slit will actually spread into regions of geometric shadow, where when these lights or these waves overlap, they will actually form interference patterns. So we shall say waves at each slit. Waves at each slit spread into the region into the regions or into the region of geometric shadow, into region of geometrical shadow, where they overlap where they overlap, or where they superpose, or where they meet. Superpose, and so on and so forth. So that is the part played by diffraction. The waves at each slit spread into the regions of geometrical shadow where they overlap or where they meet. And of course, when they meet, they form interference patterns. So where they overlap or where they meet, forming interference patterns. Then explain the reason why a double slit is used rather than two separate sources of light. Separate sources of light. A double slit would mean that the same source of light is used, but the waves just split at the double slits. But using two separate sources of light would mean there is a possibility that the light sources are not coherent. It is actually impossible to have two separate coherent sources of light. It is impossible to have two separate or independent coherent sources of light. So we can say light waves from a double slit are coherent. Light waves from a double slit are coherent. In other words, remember what we mean by coherent. They have a constant phase difference. Light waves from a double slit are coherent. It means they have a constant phase difference. Alternatively, you would simply say there is no coherence for two separate light sources. There is no coherence. There is no coherence. There is no coherence for two separate light sources. There is no coherency for two separate light sources. It's never there. But for one source passing through a double slit, it forms two secondary sources of light which are coherent. A laser emitting light of a single wavelength is used to illuminate S1 and S2 as shown here. These are double slits, so you know what it means. Okay, so this is D, this is the slit separation A. An interference pattern is observed on the screen AB. The separation of the slits is 0.48 millimeters. The slits are 2.4 meters from AB. The distance on the screen across 16 fringes is 36 millimeters. Across 16 fringes. Okay. Calculate the wavelength of the light emitted by the laser. So we want use, of course, the equation lambda is equal to Ax over D. The only challenge is going to be D. D is the distance between two successive bright fringes or two successive darker fringes. So let's just count. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you see each distance between two successive is x. So we have that 16x is equal to 36 millimeters, which means x is 36 divided by 16. X is 36 divided by 16, which is 2.25 millimeters. 2.25 millimeters. So I just substitute. They gave us A as 0.448. So that is 0.48 times 10 power negative 3 meters. X is 2.25 times 10 power negative 3 in meters, divided by D, which is 2.4. So I press my calculator. And from my calculator, this is 4.5 times 10 power negative 7. You can verify. Two dipoles or dippers, D1 and D2, are used to produce identical waves on the source of water as illustrated here. So we have dippers D1 and D2. So they are like two sources of waves. However, you see that the distance of a wave from D1 to P is 7.2 and the distance of a wave from D2 to P is 11.2 centimeters. There is a path difference. Let's find the path difference here. So path difference is going to be 11.2 minus 7.2, which is 11.2 minus 7.2, which is 4. The path difference is 4 centimeters. Okay. What is the wavelength? The wavelength of the waves is as 1.6 centimeters. So if path difference is 4 centimeters and wavelength is 1.6 centimeters, we can divide. Path difference, lambda, sigma divided by lambda is 4 divided by 1.6, which I think is 2.5. 2.5. So you will see that path difference is equal to 2.5 times lambda. Let's see the questions now. The phase difference between the waves produced at D1 and D2 is 0. That is at the source. The phase difference between the waves from the source is 0. State and explain what is observed at P. Although the phase difference is 0, the path difference at P is not 0. So it means even the phase difference at P is not going to be 0, because the waves are not traveling the same distance to reach point P. So we have seen that the phase difference is 2.5 lambda, that is destructive interference, because 2.5 is not a whole number. If it was a whole number, then it would be constructive interference. And by the way, the phase difference corresponds to 2.5. Phase difference. Phase difference, remember lambda stands for a full cycle, which is 360. So phase difference can be 2.5 times the 360, which I think is 900. Is it? 2.5 times 360, that is 900 degrees. Or because lambda is 2 pi in radians, so 2 pi times 2.5, that is 5 pi radians. That is the phase. Phase is in terms of angle. Phase difference is 900 degrees or 5 pi radians. That is destructive interference anyway. So at point P, because destructive interference is occurring, we expect no disturbance of water, we expect no movement of water. Destructive interference has occurred. So no movement, no movement of water. Or you can say no disturbance or no disturbance? The reason is very simple. The path difference is 2.5 lambda, or you can say the phase difference, is 900 degrees or 5 pi radians. So destructive interference occurs. So it's like a crest is meeting with a trough. That is destructive interference. Therefore, if a crest is meeting with a trough, we don't expect movement, or we expect very little movement. If the waves had the same amplitude, because the waves were identical, then it means they have the same amplitude. Therefore, there will be no movement completely. The amplitudes are the same, so total cancellation occurs when there is destructive interference. State and explain the effect on the answer to C Roman 1 if the apparatus is changed so that separately, number 1, the phase difference between the waves at D1 and D2 is 180 degrees. Initially, they were in phase at D1 and D2, but then the phase difference has been changed to 180 degrees. What does that mean? If it has been changed from 0 to 180 degrees, it means where we expected a minimum previously, we are now going to see a maximum. So what has happened? Perhaps there has been a swap. There has been a change in positions. So where we have a maximum, we have a minimum at P, we are going to expect now a maximum. Where there was no movement of water, this time there is going to be a maximum displacement. So there will be the water at point P is going to actually vibrate. So since path difference is 2.5, but one wave is initially half a cycle ahead of the other, then they arrive in phase. So water at P vibrates. So we simply say water at P vibrates. Water at P vibrates, and what does that mean? Constructive interference has occurred. In other words, there has been a swap. There has been a swap of positions of maximum and minimum. So since path difference is 2.5, since path difference is 2.5 lambda, but one wave is initially half a cycle, half lambda ahead of the other. So they arrive in phase. One wave is initially a half a cycle, half lambda ahead of the other. Then they arrive in phase. They will simply arrive in phase because 2.5 plus 0.5, that is a whole number, or even if you say 2.5 minus 0.5, it is still a whole number. That is constructive interference. So the path difference will be 0 when they arrive at point P, in case the sources are now 180 degrees out of phase. So in other words, there will be a swap in the maxima and minima. So water at point P now vibrates with the maximum amplitude. Then the intensity of the wave from D1 is less than the intensity of the wave from D2. Remember, this is done separately. So if the intensities have changed, of course, destructive interference will still be there, but this time we don't expect there to be zero. We don't expect to be zero movement. Since the amplitudes are not the same, there is no total cancellation. Therefore, there is some vibration, but it's very small. Therefore, as amplitudes or displacements are no longer equal because intensity is directly proportional to amplitude squared. So as amplitudes are no longer equal because the intensity is not the same, amplitudes or call them displacements are no longer equal. Are no longer equal. They do not cancel. They do not completely cancel. So the surface or the water at P vibrates. Although it may vibrate with a smaller amplitude, it still vibrates. The water at P vibrates. I will just say in brackets, although with small amplitude. This is just an addition. It's just by the way to make it to add more clarification. A diffraction grating is used to determine the wavelength of light. Describe the diffraction of light at a diffraction grating. Describe the diffraction. Of course, diffraction means the waves are the slits spread into the regions of geometrical shadow. The waves, because the diffraction grating is made up of many slits, the waves at the slits spread into the regions of geometrical shadow. That is the diffraction of light at the diffraction grating. The waves at the slits spread into regions of geometrical shadow, of course, forming interference patterns. By reference to interference, explain the zero order maximum. When we have a zero order maximum, and remember this is the central order maximum. For this one, remember the path difference is zero, the phase difference is zero, the waves travel the same distance from the sources to the point. So they travel the same distance, the phase difference is zero, giving us a zero path difference. That's when we have a zero order maximum. So waves from each slit waves from each slit, let me say overlap or meet, or we can say superpose. It is the same thing, you just choose one. The waves from each slit overlap or they meet or superpose with a phase difference of 0. With a phase difference or path difference of 0. Waves from each slit overlap or meet or superpose with a phase difference or path difference of 0. Then by reference to interference, explain the first order maximum. First order maximum. Remember, maximum, that is constructive interference. For constructive interference, the path difference is going to be n times lambda. Remember, lambda is one cycle. That means the phase difference is going to be n times 360 degrees, or it is n times 2 pi in radians. That is for constructive interference. So since it is the first order, n is 1, so the path difference is going to be lambda. The phase difference is going to be 360 degrees or 2 pi radians. So here, the path difference is wavelength. Path difference is equal to wavelength. Path difference is equal to 1 wavelength. The path difference is equal to 1 wavelength, or the phase difference is 360 degrees, or it is, since n is equal to 1, it is 2 pi radians for the first order maximum. For the second order, n would be 2. The path difference would be twice wavelength. The phase difference will be 760, and so on and so forth, or 4 pi radians. A diffraction grating is used with different wavelengths of light. The angle theta of the second order maximum is measured for each wavelength. The variation with wavelength lambda of sine theta is shown in the figure. Maybe just to remind ourselves of a diffraction grating for those who don't know. For a diffraction grating, d sine theta is equal to n lambda. They have sketched a graph of sine theta against lambda. So it means sine theta should be equal to n over d times lambda. Compare with y equals to mx plus c. On the y-axis, we have sine theta. On the x-axis, we have lambda. So the gradient is n over d. Let's see the questions now. Determine the gradient of the line shown in the figure 5.1. We just want the gradient. Okay, that is very easy. So we shall choose, since the line stops at the extreme points, we can choose this point here. And that point there, I'll put there my ruler and see if it is exact. Yes. So this one is on the scale on the vertical is 0.2 minus 0.1, that is 0.1 divided by 10, that is 0.01. So this is 2.0.2, I think 2930. So this is 228, and this is 0.41424344, 0.44. Then on the x-axis we have 350 and 550. So the gradient is going to be equal to the y-axis. We have 0.44 minus 0.28 divided by, you can choose other points for the gradient. So divide by 550 minus 350. So 0.44, 0.28 divided by 550 minus 350. And this is 8.0 times 10 power. Because on the x-axis, this one is 10 times 10 power negative 9, because it was in nanometers. And on the y-axis, it is a ratio, so there are no units there. So this will be times 10 power 5. Use the gradient determined in Roman 1 to calculate the slit separation d of the diffraction grating. Remember, we have already established that the gradient is equal to n over d. Gradient is equal to n over d. We have already established that. So d sine theta is equal to n lambda. And we have seen that the gradient is n over d. So the gradient is 8.0 times 10 power 5 is equal to n. Which order is that? The angle theta of the second order. So n is 2. So n is 2 divided by d. So d is 2 divided by 8. And d is 2.5 times 10 power negative 6 meters. On the figure 5.1, sketch a line to show the results that would be obtained for the first order, n equals to 1. You see that the gradient is directly proportional to n. So if n is first order, then if n is first order, it means the gradient is going to be half of that of second order. The gradient is going to be half of that of second order. What does that imply? So we are going to find a gradient which is half of, so the gradient of the new one should be around 4.0 times 10 power 5. So we are going to draw a graph which is less steeper than this one. Less steeper than this one. I can check how I can do it easily. Let me see. So 0.22. Perfect. So I'm just going to divide these values on the vertical by 2. This one by 2 to be 0.14. So 0.121314 is here. So 1, 2, 3, 4. So that will be the point. Then I divide the 0.44 by 2. 0.44 by 2 is 0.22. So 0.22. 0.22. 0.202122 is here. So this will be the point. Therefore, I will draw my graph in those 2 points. Okay, so that is my graph. You can check the gradient and see if it is half of the other one. So if I have 0.22 minus 0.14 divided by 550 minus 350. I can check that one. 0.22 minus, remember this is times 10 power negative 9. 0.22 minus 0.14 divided by 550 minus 350. This gives me 4.0 times 10 power 5 as the gradient. So I think since the gradient is directly proportional to n, when n was 2, gradient was 8. When n is 1, the gradient is going to be half. Therefore, my graph is perfectly correct. My graph is correct. So gradient is directly proportional to n, so the new line has half gradient. Half of the original gradient. That is 4.0 times 10 power 5. Okay. One end of the string is attached to a vibrator. The string is stretched by passing the other end over a pulley and attached on a load, as illustrated in the figure. So we can see the diagram. There is point A here and point B here. We see 1, 2, 3, 4, 5 loops. The frequency of vibration of the vibrator is adjusted to 250 Hz. A transverse wave travels along the string with a speed 12 meters per second. The wave is reflected at the pulley and a stationary wave forms on the string. Figure 4.2 shows the string between points A and B at t equals t1. So at t equals t1, we are seeing a stationary wave. And at t equals t1, the string has maximum displacement. So this graph is showing maximum displacement of a stationary wave at t equals t1. That is, constructive interference has occurred at t equals t1. So we are starting with maximum displacement. Calculate the distance between A and B. We just go back to the graph. A half plus a half plus a half, 3 halves. That is 3 over 2, that is 1.2. So the distance AB, this distance L is representing 3 over 2 wavelength. So distance is equal to 3 over 2 wavelength or 1.5 lambda. But what is the wavelength? From the general wave equation, wavelength is equal to V over F, and V is 12 meters per second, and F was given as 250. So it means the distance is going to be 1.5 times the wavelength, which is 12 over 250. 1.5 times 12 divided by 250. So that distance is 0.072 meters. On the figure 4.2, sketch the position of the string between A and B at times t1 plus 2 milliseconds. What is 2 milliseconds, first of all? Remember, t1 is like our starting point when we had maximum displacement. But then how about t millisecond, 2 milliseconds? First of all, the frequency was 250. What is the period? The period is 1 over 250, which is equal to, I think this is 0.004 seconds, which is 4 milliseconds. And then we are looking at time, which is the starting time plus half a cycle. 2 milliseconds, this is half a period. So in other words, the starting point plus half a period. Half a period means one wave has moved half a cycle on one side and the other wave has moved half a cycle on the other side. Therefore, the path difference between them is a complete cycle. The phase difference between them is a complete cycle. And when the phase difference between the two waves is a complete cycle, that means constructive interference has occurred. The phase difference between the two waves is 360 degrees. It is a complete cycle, or the path difference is wavelength. 2 milliseconds is half a period, that is half a cycle. One wave has moved half a cycle on one side, the other wave has moved half a cycle the other side. One wave has moved half a cycle to the other side from T1. The other wave must also have moved half a cycle the other side from T1. So it means they are half a cycle and half a cycle apart, which means they are a full cycle apart. Half a cycle from the starting point and half a cycle from the starting point, which means it is a full cycle apart. And whenever two waves have a full cycle apart, then constructive interference has occurred. So constructive interference, but this time it is going to be reversed. Therefore, we shall have a wave which is similar to the one which is already there, but this time it is in the opposite, on the opposite side. So we shall have something like this. For easy drawing, let me draw a horizontal line here. I will use draw dotted for easy reference. So we shall have something, some wave like this. So they said label this P. So we are labeling this one P. Then at t equals to 5 milliseconds, you see 5 milliseconds is one cycle plus a quarter a cycle. One cycle plus a quarter cycle. It means one wave is one cycle on one side and the other one is one cycle on the other side. That one would cause constructive. But again, there is a quarter. A quarter on one side and a quarter on one side. This gives us a half cycle apart. So here it means the two waves are a quarter plus a quarter, which gives us a half a cycle apart. Whenever two waves are half a cycle apart, it means a crest and a trough are meeting. That is destructive interference. The phase difference here is 180 degrees. Because of this quarter here, because 5 milliseconds is 4 plus 1 millisecond. 4 is a full cycle and 1 is a quarter cycle. So this quarter here, it means one wave is a quarter from the starting point. The other is also a quarter from the starting point. So they are a quarter plus a quarter apart, which is a half a period apart or half a cycle apart. The phase difference is going to be 180 degrees, and this is destructive interference. Whenever there is destructive interference and the waves are perfectly identical, total cancellation occurs. Therefore, the resultant displacement is zero. So in that case, for the second part, we shall simply have a horizontal line because the particles will be permanently at rest. So this will be a horizontal line. So we shall call this one Q. We call that one Q as required. And I think that is all. Next, describe the Doppler effect. Describe the Doppler effect, or describe what is meant by Doppler effect. By the way, for this particular question, we just needed to know where the 2 milliseconds relates, how the 2 milliseconds relates with the period, and how the 5 milliseconds relates with the period, for you to be able to answer that question. Okay, describe the Doppler effect. Describe the Doppler effect. What do we mean by Doppler effect? Of course, we know that Doppler effect is the apparent change in the frequency of sound due to relative motion between the source and the observer. Apparent, it may not be actual. Apparent change in the frequency of sound due to the relative motion between the source and the observer. That is Doppler effect. When the source moves towards the observer, the observer gets an impression that the frequency is higher. And when the source moves away from the observer, he gets an impression that the frequency is lower. A car travels with a constant velocity along a straight road. The car horn with a frequency of 400 Hz is sounded simultaneously. A stationary observer on the roadside hears the sound from the horn at a frequency of 360. You see, 360 is less. The speed of sound is 340. Determine the magnitude v and the direction of the velocity of the car relative to the observer. Because the observed frequency is less than the normal frequency, then the direction is away from the observer. Away from the observer. That is the direction. So let's find the velocity. So the observed frequency is going to be v over v. Since the observed frequency is less, the denominator will be plus the speed of the source, which I'm calling us, times f of fs. Here now, what we normally use as v is not the v they want here. This is a different v, which is the speed of light. The v they want is actually what we normally replace with us. But that one doesn't mind, that doesn't affect anything. So observed frequency 360. Note that the v here in the expression is not the v they want, it is the speed of sound. But this is how it is quoted in the list of formula. So this is going to be 360, 340. So this is 340 divided by 340 plus the speed which we want, I'm calling it us, times the normal frequency, which is 400. Normally we find challenges with solving this, but a mathematician would simply see that this is 340 plus us equaling to 340 times 400 divided by 360. So mathematician will simply say 360 times 340, 340 times 400 divided by 360. Then we'll take 340 to the left, to the right, so that is minus 340. And that is 37. So I'm finding us, which is our v for this particular question, and it is 37.778. So which is approximately 37.8 meters per second. Okay, A child sits on a rotating horizontal platform in a playground. The child moves with a constant speed along a circular path, as illustrated in the figure. So note that at P it is towards, at Q is away, the other side is downwards, the other side is upwards. An observer is standing a long distance away from the child. During one particular revolution, the child, moving at a speed of 7.5 meters per second, starts blowing a whistle at point P. Note that at P is moving towards and stops blowing it at point Q on the circular path. At Q is moving away. The whistle emits sound of frequency 950 Hz. That is the normal frequency. The speed of sound in air is 330. Determine the maximum frequency of the sound heard by the distant observer. So maximum frequency must be heard when the child is at point P, because at P is moving towards. Therefore, frequency F naught is equal to V over V plus US. Because maximum frequency is when it's towards, that will be plus. Actually, it will not be plus, it will be minus, so that the denominator is smaller and the frequency will be higher. So this is minus, then times Fs. So this is going to be, the speed is 330 times Fs, which is 950, divided by 330 minus US, the speed was 7.5. So what is the frequency here? 330 times 950 divided by open bracket 330 minus 7.5. So this is giving us the maximum frequency as 972.09, which is approximately 970 Hz to two significant figures. Describe the variation in the frequency of the sound heard by the distant observer. Of course, the frequency is going to vary. It will increase and decrease. Increase above 950, or it increases to 970 as the child moves towards, that is at point P, and goes to below 950 as the child moves away, that is at point Q. And of course, at Q it is going to be 930. So the frequency decreases from 970 Hz to less than 950 Hz. That is to about 930. That is the minimum. To about 930 Hz continuously. Because the child is moving continuously, the frequency decreases from 970 to less than 950 Hz continuously. That is what is going to be observed by a distant observer, because he starts blowing a whistle at point P and stops at point Q. So at point P, the frequency is 970. At point Q, the frequency will be 930. So the frequency decreases from 970 Hz to less than 950 Hz. That is to, of course, here it will be 950. Here it would be 950 if it was to continue. But here it is 970 because it is towards. Here it is 930 because it is away. So the frequency decreases from 970 Hz to less than 950 Hz, that is to 930 Hz continuously as the child moves. Okay, so for part 2, I beg to stop here on page 471. Part 3 will start from here. Have a blessed day and Happy New Year.